Welcome back. In this session, we're going to be talking about Newton's law of universal gravitation. Newton's law of gravity, whatever, but it's the universal law because it covers basically the covers space, the galaxies and the stars and all that stuff. Now, how do we start this? Let's just start it slightly differently to maybe some textbooks. I'm not saying that is, but I sort of look at it and I say, but hold on. Here I am stuck on the planet Earth, and I know that my weight is equal to Fw or Fg is 9.8 meters per second squared times my mass. This is acceleration due to gravity, right? Yes, this does make me think of that literary work, The Little Prince or whatever it is, where he's standing on a star. Now, what does it mean? This is the force that I am being pulled towards the planet with, the center of the Earth, actually. So we take everything here is taken, okay, we measure from the center of the object, okay? Right? You've heard people say it's got a high or a low center of gravity. That's kind of fictitiously where if we placed all the mass, all right? That's really what it means. Now, what are we saying here? We're saying that we're measuring everything to the center. So that's the force. But now, what Newton's law says is this. It says that every object, okay, that's got, and you must learn the law, right? Every object has got a mass, right? Now that doesn't change as our mass can change, okay, if we lose weight, right? But we're actually not, we're losing mass, okay? So what are we saying here? We're saying that this object here and this object are actually attracted to each other. And that force, okay, just to put Newton's law down, you've learnt the definition at this stage, obviously. Yep, you have, hey? Good. So we say, right, the force is equal to G times M1 times M2 over R squared. Please be careful. R equals distance, center to center. R is not radius, okay? R is distance center to center. Please be careful with that. Okay, I've said that now 3 times. I will no doubt say it again. Because that's an error that I see all the time. They talk about radius because it's going to come in as a radius as well. Now, let's have a look here. So what have we got? We've got these objects of mass. Now, bearing in mind, we're talking about moons, planets, suns, quasars, pulsars, binary systems, okay? Trinary systems, where you've got 3 of them. Talking about entire galaxies, right? We're talking about black holes, right? We're talking about the dark matter and the dark energy that's out there. Okay, that's not Star Wars, but we're talking about all of those things that are out there in the universe. So we say that the fact that these have got a mass, they're going to attract. Now, this section is predominantly about proportionality. So let's just have a look here. Force, and Kevin goes and writes an equal sign. The force is proportional to M1 times M2, which is the product of their masses. Okay, that's in the definition itself. The force is proportional to, same force, 1 over R squared. So it's inversely proportional to distance squared, right? Then what is G? G is the constant. And it's given the value, and yours truly has written it down here somewhere, 6.67 times 10 to the minus 11, and that's got a whole bunch of units behind it. You are given that. You don't have to remember it. Okay, So we say righty-ho. In essence, what have we got? We've got our things. Let's just say what we've got here is we've got two, I don't know what you want to call it, two planets, all right? Two heavenly bodies that are out there. And this planet and this planet are a distance r apart from the centers of the planet. So remember, how are they going to mess you around in a test? They're going to give you the diameters and the surface to surface distance. Just have a look at this. I know, but this is the kind of things to remember. Here's my pink planet. Here's my green planet. Then they tell me the diameter of this planet and the diameter of that planet. And they tell me the distance there apart. Remember, when we are working with our Newton's laws, we are measuring from there to there. So I've got to add the radius of the planet, radius of the planet 2, okay, plus this distance here. All right. So once again, yep, I know, I'm boring, I know. It's draw it, especially these. These are critical to draw because if you draw them, you can immediately see what you have to calculate because of the way these questions are asked, all right? And we're going to do some examples of these now. So, all right, let's now say we've got that situation like this. Let's just consider something now, all right? We've got mass 1 and we've got mass 2. Now, they are, there we go, that's R. And what do we measure this in? Here's the next trick. We measure it in meters. But do we measure distances in planets in meters? No. You measure it in kilometers, okay? Or parsecs or whatever you want, okay? Clicks. So what are we saying? We're saying that we must convert to meters straight away, okay? Don't leave it because you're going to be squaring it. So therefore, you need to get it to meters. Do we measure planets' mass in kilograms? No. We measure it in tons. All right? For those of you doing this in other than the metric system, okay, you're going to be converting it to pounds. Right? Tons. Well, ton is what? Well, here we go. 1 ton is 1,000 kilograms. So step 1 is convert masses and distances to kilograms and meters, because it's kilogram meters per second squared. Now, or kilograms, meters, and seconds. Right. Then we say, all right, okay. Essentially, if I write the formula down, all right, the formula is going to then be F, force between them, is G times M1 times M2 over R squared. Now, let me just slide my paper down a little bit. Okay, feels odd saying a screen, but there we go. Okay, we've got, that's the force of attraction. Next trick question that comes up, okay? Time and time again. The two forces, they are the same. Just opposite directions. Right? They are the same force. Why are they the same force, you ask? Why does the big planet not have a bigger force on the little one than the other way around? Well, because let's have a look at what the formula says. Let's look at it simplistically here. All right? Let's say the force from A to B, planet A to B, is G times M of A times M of B over the distance squared. Then what is the force from planet B to A? Is G times the mass of B, and you can probably see where this is going, can't you? Over, radius squared. I do that a lot. Radius squared. It is the same. Okay? So when you ask that question, it will be a multiple choice question. You say they are the same but opposite directions. They very often will give it to you if you look they'll give you a drawing like this, and they'll say, pick an arrow that way, an arrow that way, an arrow that way, an arrow that way, and then two that are the same. That's the one. They are the same force, equal but opposite direction. Okay? Okay, does that mean equilibrium? No, because equilibrium is based upon the forces on a single body. So this planet and this planet are pulling each other together. But hold on, why are they not then like that? Well, because there's other forces acting in the universe contrary to those, all right? So no, it's not a case of that's going to happen. You'll see when we talk about the moon and the earth in a few minutes, or asteroids and stuff. All right? So then we say, given any of the information, we can find the other information. Okay, the questions are usually, let's just do an example, shall we? Okay, this is a typical example out of a dozen books, all right? I've looked through them. They say, all right, two objects of mass m, m1 and m2, attract each other with force F. Okay, so we've got two objects, m1 and m2, okay? And they attract each other with force F, okay? Force F and force F, okay? And they are a distance r apart, okay? They say, then what happens to FF? Okay, but hold on. What is this? Guys, this is case 1. Then you go and you draw case 2. You say, right, M1, M2. This is F1. This is now going to be force 2. Okay? And we are going to change things. Right. Let me not call that M1 and M2 and R. Because they say to us the following. They say, if I double mass 1, okay, so what did I do? Times 2. So this must be 2m1. And if I halve mass 2, I halve, so this is going to be a half mass 2. Okay? This is what happens. This is different planets now. But all I'm doing, look at the process. Case 1 and case 2. Scenario 1, scenario 2, whichever you like. All right? Then I say, what did I do to r? To the radius or the distance between them? I halve the distance. So r now becomes a half r. This is the recipe, guys. You do the drawing for case 1, do the drawing for case 2. Even if it's a multiple choice question for 2-3 marks, doesn't matter. Do a quick drawing. Okay? It's quick, but it guarantees you that percentage, done and dusted. Don't guess. Okay? Because guessing invokes a probability, which we deal with in if you're doing AP maths in grade 12s, but don't do that. Okay? It's easy to work out. I know you're going to say time pressure, time pressure. You have 2 minutes. 2 minutes to work this out. Draw that, draw that. Okay, I've taken longer than that because I'm talking. But what do? I say, okay, F1 is equal to G M1 M2 over R squared. Then I say case 2. Let's do it in red. F2 is equal to what? Is equal to G times 2M1 times a half M2 over a half R squared. Well, whoopee-doo, what do we do now? Then we just remove the brackets. We get F2 is equal to 2 times a half divided by a half squared, correct? Multiplied by G times M1 times M2 over R squared. All I did was I took out the numbers. Okay, go with me. There's the 2, there's the half, and there's the half. I applied the square to both terms inside. Can you see that? Well, I'm sure you can. What do I do next? Next, I say, okay, I simplify this. That's 1 over a half squared is 1 over a quarter times G M1 M2 over R squared. What is this? This is going to be equal to 4. And the final trick in the scenario here is, look here. Okay, blue. F1 is that. Okay, let's go and find it. Down the page. Okay, hello, there it is. There you go. So that's 4 times F1. So F2 has gone up by 4 times. Can you see that that it's very simple to work it out? Initially, it looks very complex, but it's not. Okay. The second part of this chapter, and really I've been through the books, just follow what I'm saying to you, and they're very simple, straightforward, okay? Let's look at the next situation. The next situation is there's the center, and here you are out in space, whirling silently in space, right? Okay. Could have put a smile on that one's face, couldn't I? Right, now that's a radius apart. So the planet, the force between both, because don't forget, this one attracts this one as well, huh? So what do? We say, whoa, the force between the astronaut is also pulling the planet. Yeah, okay, well, yeah, but not that much. Is G times mass of the planet times mass of the astronaut over radius squared. Right. Now, that's cool. Let us now say, let's take the next step with this then and say, cool. Let's put this person on the Earth or on the planet, right? So what can I say? All right, I say, right, this is the distance that we are away. This is actually the radius of the planet. What is the force? The force is G, mass of the planet, mass of the astronaut, over radius of the planet squared, correct? All I've done, M1, M2, radius, because I'm standing on the surface now. Okay. But just hold on. What did we say right at the beginning when I spoke about the little prince? The force is the same, is also equal to mass of the astronaut times G. Isn't it? It's the same force. Can't be different. Okay, it's impossible to be different because I'm standing on the planet. I can't have two forces pulling me to the planet. It's got to be the same one. Here I am standing on, here I am standing on the planet. Okay, it's the same force. So I can say, therefore, mass of the astronaut times G, because those are equal to each other, is equal to G, mass of the planet, mass of the astronaut over the radius of the planet squared. Therefore, the G on any planet is equal to G times mass of the planet over radius of the planet squared. And this is where you find yourself feeling very unwanted because you don't count. Okay. This question is, show that the mass or your mass or the mass of the body is irrelevant to the calculation of G, that it doesn't feature. You don't count. All that G is, G of the planet, is the mass and the radius of the planet itself. All right. So that's pretty straightforward. Okay, there's no rocket science. The rocket science is, of course, how to defeat G. Hey, right. Let's do an example. The weight of an object. Let's do this example. Okay, where they say the weight of an object on planet Zog, okay, which is my home planet, by the way, okay, is 250 newtons. Okay. Find the weight on Earth. Find the weight on Earth. Okay. Given. Now look at this. Mass of Earth over mass of Zog is a half. Okay? And radius of Earth over radius of Zog is equal to 2 over 3. All right? And you say, oh, no, that's just terrible. Can't do that. Well, what do? Draw it. Okay. Here we go. Whoops, the daisy. That is so frustrating when it does that. Here we go. This is Zog. And this is Earth. Okie dokes. Right. So now I know that F on Zog is equal to 250. And we're looking for F there, aren't we? Now, G, hang on. This is equal to G of Zog multiplied by mass. This is equal to G of Earth multiplied by mass. But G of Earth is known, is 9.8 times mass. So if I can find mass, I can work out what the weight on Earth is, can't I? So let's start off. G on Zog is equal to G times mass of Zog, radius of Zog. Okay? And G on Earth is equal to G times mass of the Earth times radius of the Earth squared. And I always forget to square these things. Okay? Right. But now, okay, let's just have a look. Take the ratio of G of Zog. Okay? Look what I did. I combined these. I combine like that. Use a ratio. I said G of Zog divided by G of Earth. And they are all the same. When you've done one or two of these, you'll see they're all the same. Okay, G of Zog of G of is equal to G times mass of Zog over radius of Zog squared over G times mass of the Earth, radius of the Earth squared. Can you see I just took the one, that's Earth there by the way, I just took the one and divided by the other. Well, that helps me in a sense because it allows these to cancel out. All right. I am then left with the following. That is going to be mass of Zog, radius of Zog squared. Divided by that means times radius of the Earth squared over radius of Zog. Mass of Zog, you sausage. Mass of Zog. Okay. Mass of the Earth, in fact. Right? All I've done is I've tipped times this guy because I'm dividing by it. Okay. Please make sure you get that element under your belts. It is very often this section trips people up on just basic grade 7 or 8 maths. All right. So the ratio of the two. Now hang on. Look here. Mass of Zog, mass of the Earth multiplied by radius of the Earth squared over radius of Zog squared, which is the same thing as mass of Zog, mass of the Earth multiplied by radius of the Earth, radius of Zog, all squared. I mean, do you know, let's be honest, it looks pretty cool when you're writing these formulas out, doesn't it, to somebody who doesn't do physics. Only we know they're not as difficult as they're made out. But to everybody else, it's, oh my goodness, eh? It is kind of a cool thing. Let's be honest. Okay, so then I can say, therefore, G on Zog over G of Earth is equal to, and I work that out, it's going to be 2 over 1 times 2 over 3 squared, which gives me 8 over 9. Therefore, G of Zog, okay, is going to be equal to, well, let's just, before we do that, just give me a sec. Let's cross multiply this. I can say 9 times G of Zog is equal to 8 times G on Earth. Therefore, G of Zog is going to be 8/9 G of the Earth, which is 8/9 times 9.8, which is going to be equal to 8.71 meters per second squared. Right? That is G on planet Zog. Right? Now, what did I want? I wanted to work out the actual mass. I said the weight was 250 newtons. So 250 newtons must be equal to M multiplied. Now remember, I'm on Zog. Okay, mass times 8.71. Therefore, the actual mass is going to be equal to, can you believe it? I didn't work it out. All right, well, let's work it out. So the mass is going to be equal to, I thought I had, you know. Never mind. So the mass is going to be equal to 250 divided by 8.71, which is going to be equal to 28.7 kilograms. Therefore, on Earth, FW, the weight is what they asked us for, is mass times G, which is going to be 28.7 times 9.8, because I know G of the Earth. It's a known. So it's 28.7 times 9.8 is equal to 281.3. Done. Okay. Right? Clear that off. So there we go. Let's look at another example, shall we? Another example of this. Put this pen out my way. Another example of this. Let's look at this. It says here an asteroid approximately spherical. Okay, approximately spherical with a diameter equal to 1 kilometer. Okay, a density, this is different, density of 7850 kilograms per cubic meter. That, by the way, is mainly iron. Okay, is 500,000 kilometers from Earth. Okay, Earth diameter is equal to 12,740 kilometers, and mass of the Earth 6 times 10 to the 21 tons. 6 times 10 to the 21 tons. Calculate 1. Force of attraction between the Earth and the asteroid. Earth and the asteroid. Okay. Number 2, the force of attraction between the asteroid and Earth. Question 3. Okay. The acceleration. Yep, I hope you've got F equals ma in your mind. Acceleration of the asteroid towards Earth, and for the acceleration of the Earth towards the asteroid. Okay, right. How do we do it? Hello. We've got to draw it. But first, why are they telling us it's spherical with a density? Because let's have a look. Let's just draw it first, shall we? Okay. Sorry, I'm going over a bit much. It won't take me like 3 minutes, I think, to finish this. We say, all right, here we've got the Earth. And here we've got the asteroid. Okay. And they've told us that that is 500,000 thingy, and it is surface to surface. Okay, so let's put that in there. And we said it was 500,000 kilometers from surface to surface. They gave us diameter of the Earth, 12,470, I think. Oh, 740 kilometers. So hang on, look at this now again. Right, here we go. I need that, and I've got that, but we also need that to get to the center, don't we? So we've got mass of the Earth over here is 6 times 10 to the 21 tons. Mass of the asteroid, we don't know. Oh dear. What are we going to do now? Well, we now have to go and do a little bit of work. We have to calculate the mass of the size of the asteroid. They have told us that the density, which is rho, is 7850 kilograms per cubic meter. Density is equal to mass over volume. They've told you it's mass over volume. That's what it's worked out as. So we say that is equal to 7850. But they've also told us on this thing, have a look, okay? They've told us that it's got a diameter of 1 kilometer. That's 1,000 meters from there to there. So can I work it out? I say, okay, my mass of the asteroid, okay, is going to be 7850 times the volume. What's the volume of the ball? Is 4/3 pi r cubed. Okay? Why am I doing this? Because this is one way of asking it to make it bigger marks. Okay? It's very difficult to get high marks out of this because there's not a lot to it. But by putting this in, yeah, there is, because now you've got to know quite a bit to be able to get it. So therefore, but now I know r. So it's 4/3 pi times radius is 500. But whoa, 500. It's 500 meters. Okay. So we say, okay, 500. That was a kilometers, 1,000. So 500 cubed. Okay. So now you can see. Let's have a look. So that's going to be 500 cubed. 500 to the power of 3 is that. Times shift pi equals that. Times 4 equals divided by 3 equals. And it gives me a number of 52359. Okay, 8775 cubic meters, right? Now, how do I work out the mass? Well, there it is. So, therefore, it's going to be 7850 times that number there, which gives me a mass, just hold on, times 7850 is going to be equal to 4.11 times 10 to the 12. All right, so that is the mass in kilograms of this thing. Now I can go back up and I can say, okay, I've got you. You are 4.11 times 10 to the 12 times 10 to the 12 kilograms. Okay, then all I do is I plug that into the formula and let's write it down. F is equal to 6.67 times 10 to the minus 11 multiplied by 6 times 10 to the 21 times 1,000. Where does that 1,000 come from? That is tons to kilograms multiplied by 4.11 times 10 to the power of 12. Okay. Divided by, and now we say, okay, well, let's go back. Okay. We say, let's have a look at this on our drawing here, shall we? This distance here is going to be 6370 and 123. This is going to be times 1,000. So it's going to be 500,000. 1,000. And that little bit there is going to be, well, we said so it's R is 500 meters. Okay? See that? Finally, therefore, the last thing, we can put that total number in. It's going to be 6370,123 plus the 500, 3123. That plus my 500, and let me work that out. That is 6370,123 plus 500, 123, 123 plus 500 is going to be equal to that. And then I have got you square it. X squared equals 2.56. This is 2.56 times 10 to the 17. Now I can calculate it. And I say, okay, 6 times 10 to the 200, 6 e to the x 21 times 1,000. There, I've got that. Times 4.11, 10 to the 12 equals that. Okay? Times 6.67 e to the minus 11 equals that. Divided by 2.56 to the 17 is equal to, and I get the force of 4, and I'm just going to 40457. Okay, 81250 newtons. Let's just take that 3, 6. So let's say 4.046 times 10 to the 9 newtons. 369. Okay, let's put that as that. So that's the force of the attraction. And the question, the other part is, what's the force of the meteorite on the Earth? It is the same but opposite direction. Okay. The next one is then, what is the acceleration of the asteroid? Okay, simple, and this is probably one of the longest ones I've ever done. Okay, acceleration of the asteroid, you've got the force, 4.046 times 10 to the 9 is, what's the mass of the asteroid? Hang on, we worked it out. The mass, 4.1 times 10 to the 12. 4.11. Therefore, the acceleration is going to be equal to 4.046, divide that by 4.11 e to the let me check, e to the 12, yes. Let's just make that neat, 12. Whoops, 10 to the, I've got, whoops, 10 to the 12 is equal to 9.8 times 10 to the minus 4 meters per second squared. Guys, I went through it quite fast. You can check my arithmetic, but that's the way it's asked. Those are the kind of questions that you're going to get. Just follow the recipe, draw it, put in what you're given, and work out if it's 2 planets, the G value, and take the ratios, just as I did there. There's 1 or 2 in the textbooks that use that, and the otherwise is the kind of one I've just done. Okay. Cheers. Have a great one. Enjoy Newton's law of universal gravitation, and wherever you are in the universe, it's pretty much going to apply to you. Cheers. Bye.